doke. Let's begin. So, first of all, I know that this slideshow seems huge. We're not getting through it all today. These are going to be the slides we're working on for the rest of the week. Okay, use substitution is a horribly important topic, so we're going to take our time on it. Okay, so some announcements. It's going to be a quiz. Provided I get through everything, there's going to be a quiz class. Again, provided that I get through everything that I want to. And don't forget about my office hours. If you have any questions about the class, your grade, how any sort of topic in this class, make sure to stop by office hours. Those are tomorrow and Friday, 1 to 3. I'm also in the MEC today from 10 to or whatever hour I'm in there. I forget. What hour am I in there? I'm in there at 11. Thank you. Is it another quiz? Yes, there's going to be a quiz every day this week, or every day that we have class this week, in place of homework. Okay. All right. Any questions about this? All right. Well, let's pick up and do a little bit more of what we were talking about yesterday. So first, let's find the average value of a function on the interval -3 to 3. Okay, we're finding the average value of f of x is 9 minus x cubed on this interval. Okay, so a good warm-up from what we did yesterday. So how do I find the average value of this function? And by the way, I'm going to call it f av, which is pretty standard. 1 over b minus a, and b is +3, a is -3, so 3 minus -3. Good, good start. Times what? -3 to 3, good. Yeah. The integral from -3 of 9 minus x cubed dx. Very good. So then we just need to actually work out this number. Okay, so this is equal to 1 over 3 minus -3. That's 1 over 3 plus 3, which is 6, or 1 over 6 rather. And then I need to, well, I can break up this integral into 2 pieces, right? This is the integral from -3 to +3 of just 9 dx, and then plus the integral from -3 to +3 of -x cubed dx. So I can bring this 9 out in front here, and I can bring this minus out here. And so when I do that, I'm going to end up with 1 over 6 times the integral, 9, oops, sorry. No, I pulled that 9 out. 1 over 6 times 9 times the integral from -3 to 3 of just 1 dx minus the integral from -3 to 3 of x cubed dx. Okay, so what is an antiderivative of just 1? Just x. Yeah, very good. So I'm going to get 1/6 is still out in front of everything, times 9 times x from the first integral. And what's an antiderivative of x cubed? Good. Minus x to the 4 over 4. I'm going to evaluate this at x equals +3 and x equals -3. Okay. Well, when I plug in x equals +3, so this is equals 1 over 6 times, well, I'm going to get 9 times 3 minus 3 to the 4 over 4. Then I subtract off when I plug in minus 3. So I'm going to get 9 times minus 3 minus 3 to the 4 over 4. So a little simplification. This is 1 over 6 times 27 minus 81 over 4 minus 27 minus 3 to the 4 is also 81 plus 81 over 4. So this minus 81 over 4 minus 81 over 4, those cancel. I'm going to be left with 1 over 6 times 27 minus 27 is 27 plus 27 is 54. Okay. And 54 divided by 6 is what? 9. Very good. So we have an average value of 9. Very good. Any questions about this? So again, this average value of this function is that number. If I draw the graph, what's happening here? 9 minus x cubed. Well, it goes through 0, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it does something like 1, 3, 1, 2, 3, 9 minus x cubed. So that is, it does something like this. It goes like that. And so the average value is the number 9, so that the area underneath this box is the same as the total area, the total signed area between the curve and the x-axis. Okay, so mashed potato theorem. All right. Very good. All right, and then one more example from yesterday. The velocity function in feet per second for a particle moving along a straight line is given by v of t equals t squared minus t minus 12 for t between 1 and 5. Okay, we're going to find the displacement of this particle and the total distance traveled by the particle over the time interval. So what does it mean that it's traveling in a straight line? Well, I mean, just draw a line and then it starts. We don't know where it actually starts, but if velocity is positive, then it's moving this way, v of t greater than 0. Or if you want, you can say it's moving the other way when velocity is positive. It's up to you. Math is great. You can do it however you want, as long as you're right. And then if it's got a negative velocity, I'm going to say it's moving to the left. Okay. This is what we're talking about when we're saying this particle is moving in a straight line. Okay. All right, so there's a displacement of a particle. How do I find the displacement of a particle giving its speed? Or sorry, that was wrong. Given its velocity. Yeah, the integral. Because remember, the displacement is just s. We're finding this displacement between t equals 1 and t equals 5. Well, displacement is just where did you end? Where s is my position function. We're not actually going to find the position function. But where did you end minus where did you start? That's displacement. Okay? Well, by the fundamental theorem of calculus, this is equal to the integral from 1 to 5 of s prime of t dt, right? You integrate a derivative, you get the original thing back. But then we know or s prime of t, that is v of t. So we need to find the integral from 1 to 5 of v of t, which is t squared minus t minus 12 dt. Okay, so that's what part A boils down to. So this is equal to, well, I'll break it up. This is equal to the integral from 1 to 5 of t squared plus dt plus the integral from 1 to 5 of minus t dt, and then plus the integral from 1 to 5 of minus 12 dt. No, this is the first fundamental theorem of calculus that we're using here. Okay, so I can pull this minus out in front, so I'm just going to use the eraser postulate to do that. I had a high school geometry teacher use that joke. I thought it was the funniest thing. And then I'm going to pull that minus 12 out in front of the third integral as well. So I'm left with 1 when I do that. I pull out this minus 12. All right, what's the integral of t squared with respect to t, or sorry, an antiderivative of t squared with respect to t?
T cubed over 3.
T cubed over 3, very good. Minus, what's an antiderivative of t with respect to t? T squared over 2, very good. And then minus 12 times, what's an integral, or what's an antiderivative of 1 with respect to t? T, very good. So I evaluate this at t equals 5 and t equals 1, and then take a difference. So t cubed is 125, or 5 cubed is 125 over 3, minus t squared. Well, when you plug in 5, you get 25, and then over 2, and then minus 12 times 5. Then I will subtract off when I plug in 1. Well, when I plug in 1, I get 1/3 minus 1/2 minus 12. And then the rest is arithmetic. So for time, I'm going to move on to the second part. Okay, I'll fill out that actual number after class. But this is really the heart of the problem. Okay, so then part 2 asks not about its displacement, this particle's displacement, but about the total time, the total distance traveled over this time interval. So how do I find, what's the difference between displacement and total time traveled? Total distance traveled, rather. Total time traveled is just 4 seconds.
Displacement would be the difference between where starting and where ending, but the total distance would be like
Exactly, exactly. If this particle starts at this point and then moves right over to here, distance, let's just say of 1, and then moves back over here to a distance back to where it started, well, its displacement is 0. It started and ended at the same spot. But the total distance traveled was, well, it traveled 1 over here and then 1 back. So it traveled 2 feet, okay? So we need to, in order to find the total distance traveled, instead of integrating v, just v of t, we need to integrate from 1 to 5 the absolute value of v of t, which is also called the speed. Well, in order to look at the absolute value of v of t, we need to look at where is t squared minus t minus 12. This is v of t. I'm going to find where this is equal to 0, so I can determine where it's bigger than 0 and where it's less than 0. Okay, so what does this, there's two ways. I mean, this is a quadratic equation. You could use the quadratic formula if you want, or we could try to factor this. So what do we want to do? Yeah, this factors pretty easily, right? What does it factor into? -4, yeah, t minus 4 and t plus 3, right? So then this tells me that the velocity function is 0. It might not change signs. It does change signs, but it's definitely 0 at t equals 4 and at t equals -3. Okay. I don't care about t equals -3. That's not in the time interval that we're looking at. So I'm going to throw this out. Not because mathematically it doesn't make sense, but because in the context of the problem, it doesn't make sense to look at t equals -3. Okay, so that means that I just need to find out what sign does v of t have for t between 1 and 4, and what sign does v of t have between t equals 4 and 5. Okay, so I'm going to make one of those charts. This is not the same thing as the first derivative chart, but I'm just trying to keep track of what sign t has between these values, or v of t has between these values. Okay. So when we've got t minus 4, t plus 3, and then v of t is the product. Okay, so what sign does t minus 4 have between t equals 1 and t equals 4? How could you check? Yeah, I need a test point. What test point do I want to use between t equals 1 and t equals 4? 2. 2 is a perfectly fine answer. So 2 minus 4, that's -2, right? So between t equals 1 and t equals 4, t minus 4 is negative. And then for t bigger than 4, I could plug in 4.5. I'm going to get 4.5 minus 4. Well, that's positive right here. T plus 3, if I plug in t equals 2, I'm going to get a positive for this interval. And then if I plug in t equals, say, 4.5, I'm going to get another positive. So v of t is negative on the interval 1 to 4 and positive on the interval 4 to 5. So then the absolute value of v of t is equal to something when t is between 1 and 4, and something else when t is between 4 and 5. So what is v of t when t is between 1 and 4? Or sorry, what's the absolute value of v of t when t is between 1 and 4?
-t squared plus t plus 12.
Perfect. Exactly right. You just take the negative of v of t, because v of t is negative here. That means we take the negative of it to get the absolute value of it. Okay, so I'm going to write it as 12 plus t minus t squared, which is just negative t squared minus t minus 12. Okay, and then for t between 4 and 5, well, v of t is positive there, so we can just look at the original function, t squared minus t minus 12. Okay, so if I want to integrate from 1 to 5, the absolute value of v of t, how should I break up this integral? Perfect. I need to look at it as the integral from 1 to 4 of the absolute value of v of t, dt, plus the integral from 4 to 5 of the absolute value of v of t, dt, because at 4, that's where things switch, right? And so this just becomes the integral from 1 to 4 of between 1 and 4, v of t is 12 plus t minus t squared dt. And then plus the integral from 4 to 5 of t squared minus t minus 12 dt. Okay. And then from there, we just use the fundamental theorem of calculus, not just, but we use the fundamental theorem of calculus and we evaluate that. I'm going to, again, I want to get to something else, so I'm going to write out what those actual numbers are after class. But this, once you get to here, that's the main sort of hiccup to the total distance traveled problems, is that you need to find where is v of t positive, where is v of t negative, and then break up the integral accordingly. Okay. So do we have any questions? Oh, that's a really good question. What if the particle switched directions more than once? It looks like it switched direction just once here. And it can switch directions more than one time. And in that case, you do need to break up the integral into multiple, even more integrals, one for every interval in which it's going in the positive, and one for every interval in which it's going in the negative direction. No shortcuts really. You just do the same thing we did, and then you have to, write out another integral for every time it switches direction. No, I wouldn't give you a question where it switches multiple times on the exam, just because it's so time intensive to keep writing out those integrals. The only way I would give you that question on an exam is if it was like, if I just wanted you to stop right here and I said, set up the integral, but don't evaluate it. Okay. So, but if I'm having you evaluate it, then no, I would only have something switch direction once, like a ball thrown in the air. Cool. All right, so that brings us to U substitution. Okay, we've talked about different integration rules. They're all based on a corresponding differentiation rule. Okay, one that we haven't talked about yet is the chain rule. So recall that the chain rule is just if I want to take the derivative of a composition of functions, so f of g of x, take the derivative of that, then you end up with f prime of g of x times g prime of x. The derivative of the outside evaluated at the inside times the derivative of the inside. Okay. Well, this gives us, if I integrate both sides of this, or if I take an indefinite integral of both sides of this with respect to x, well, what do I get on the left? If I integrate f of g of x all prime, what do I get? Think of the fundamental thing with calculus here. I'm just integrating a derivative. So what should I get back? The original function, exactly. So the very original thing that I first took the derivative of and then integrated, that's what I should get back. Okay, so when I integrate the left, I just get f of g of x. Okay, well, when I integrate the right, I don't know what I'm going to get there. This is the whole point. This is what U substitution is all about, is integrating something that looks like a composition times the derivative of the inside. Okay. So when we integrate both sides, we end up with the integral of f prime of g of x times g prime of x with respect to x is f of g of x plus c plus some constant. Okay, so this side looks, I'll admit, that doesn't look very useful at all. When am I ever going to stumble across things in real life that look like that? And the answer is actually quite a bit. We usually we'll have to do some work to make it look exactly like this, make an integral look exactly like f prime of g of x times g prime of x. But it usually can be done for a lot of integrals, so many that you're going to get used to u substitution being your go-to right when I'm going to switch it up and say, no, new rule, okay? But this is one of the most important integration rules, okay? So it's easy to see that if I'm integrating something that I know beforehand is f prime of g of x times g prime of x, well, that's definitely f of g of x plus c, just, again, the opposite of the chain rule. What's less easy to see is when I'm integrating just some function, it's less easy to see that it has this exact form. Okay? And so that's what today's going to be about, is recognizing when does an integral have this exact form, or at least when is it close enough that I can do a little bit of massaging and make it look like this form here. Okay? So let's look at an example here. Let's find the antiderivative, the general antiderivative, or the indefinite integral of the function 2x times the square root of 1 plus x squared with respect to x. Okay. So this is a classic u substitution problem. Okay. So looking at this, is there anything that looks like a composition of functions? Some function evaluated at some other function.
Square root of 1 plus x squared.
Exactly. The square root of 1 plus x squared, that is a composition, right? The outside function is just the square root of x. The inside function is 1 plus x squared, right? Well, then, if I'm looking to integrate something that looks like, I'm just going to write f of g of x for a second, f of g of x times g prime of x dx. Well, if f of g of x is this, then what would g prime be?
2x.
2x. And that's just like, we covered this up for a second. Like, we're not looking at this integral for a second. If f of g of x is this, that 2x is just coming from looking at what's the derivative of the inside. Okay? So g prime of x would need to be 2x, right? So, but that's exactly what g prime of x is for us, okay? So that tells us then that the integral of 2x times the square root of 1 plus x squared dx. Well, this integral comes from looking at f of g of x times g prime of x, right? So this is a little different than what we had back here. Back here I had f prime of g of x. Here, I know right away what the original function is, f of x, but I don't know f prime, right? I know the inside function. I can see that the derivative of the inside function is there. So I don't know what little f prime is, though. I do know that whatever it is, its antiderivative, I'm going to call it capital F. Okay? So this is equal to capital F of g of x plus c, where capital F is an antiderivative of what function? Let me erase this.
The square root of x.
Exactly. Capital F is an antiderivative of the square root of x. Okay. Why does that have to be the case? Well, when I take the derivative of the right here, I have to get capital F prime of g of x times g prime of x. That's just the chain rule. But I want this to equal 2x times the square root of 1 plus x squared. Well, this is g of x. This is g prime of x. That means that capital F prime has to be the square root of x, because I'm plugging g of x into capital F prime. Okay, so the only real work we have to do then, after we match up everything, the only real work we have to do is say, well, what is the antiderivative of the square root of x? And then I can just plug in everything I know into this, okay? So what's going to help us a ton here is to rewrite this like this. The integral of x to the 1/2. So what is the antiderivative or the indefinite integral of x to the 1/2? Good. X to the 3/2 over 3/2 plus c technically, which is the same thing as 2/3 x to the 2/3. So this is capital F of x, right? From this previous slide. Capital F of x, again, is an antiderivative of the square root of x, okay? So then I know I'm looking at something that looks exactly like this. The integral of f of g of x times g prime of x. Little f is the square root of x. G of x is 1 plus x squared. And so that means that I have to get the antiderivative of the square root of x, which we just found, evaluated at g of x. Okay? But this means the integral of 2x square root of 1 plus x squared dx, that this is equal to the antiderivative or an antiderivative of square root of x. That's 2/3 times x to the 2/3. So I want to plug in g of x into this. So 2/3 times, caught myself there, x to the 3/2. There we go. I always say something if I write something wrong. So 2/3 x to the 3/2. So 2/3 times 1 plus x squared to the 3/2 plus c. I should have a plus c up here as well. So this is the whole idea behind U substitution. At first, it's just going to be, can I match up the outside and the inside? Really, can I match up what the inside needs to be? If I can find a function somewhere in my integral that is inside some other function and such that its derivative also appears in this integral, then you're golden. Then you just need to find the antiderivative of the outside function, okay? So, do we have any questions about this? This is our final answer, by the way.
We're gonna do one, right?
Yeah, we're going to do a lot more of these. Yep. All right, so this is the whole thing. We need to be able to recognize when we're integrating f of g of x times g prime of x. Okay, so you're always trying to find, and it's almost always going to be, what's the most complicated thing going on inside of an integral. Okay, You're going to find what's the most complicated thing, and that's going to be your g of x. Okay. Then g prime of x will hopefully be making an appearance somewhere else in the integral. Okay. So once you do that, we just are able to say that the integral of f of g of x times g prime of x is just capital F of g of x, where capital F is an antiderivative of little f. And then plus some constant. Okay. So we'll see a few more examples where this is really just as straightforward as recognizing what does g of x have to be and what is g prime of x. Is that somewhere in the integral? Okay. So let's look at this example. By the way, that last example was very, very similar to a quiz problem. This example is also very, very similar to a quiz problem. Okay. So find the general antiderivative, or the indefinite integral, of 5 times e to the 5x. All right, so what function, again, I want to say this is equal to some f of g of x times g prime of x. I want to say I'm integrating something that looks like that, right? So I need to look at this and say, is there some function that looks like it's inside another function? And what do we think? Is there? Yeah. What do we think g of x has to be? What function is inside of another function? That's going to, e to the x is going to be the outside function. That's going to be f. 5x. 5x is inside of the e to the x, right? So we're going to make a guess and say g of x is 5x. Sometimes our guess will be wrong. Sometimes the thing that looks obvious is not quite as obvious as that. But for these first examples and for the quiz, it should be pretty obvious, okay? So g of x is 5x. That's our guess. That's what looks like is inside some other function. What is g prime of x then? Yeah, g prime of x is just 5, right? Well, I have a 5 there, so that matches up with this. So then what does f of x have to be?
E to the x.
E to the x, very good. Okay. So we know, again, the integral of something that looks like f of g of x times g prime of x. This had to come from capital F of g of x plus c, where capital F is an antiderivative of that outside function. Yes, exactly. The outside function is little f. So the integral, the only thing we need to find then is what is an antiderivative of little f, and then we're golden. Okay, so what is an antiderivative, or what is the indefinite integral of little f, which is e to the x?
The natural log of x.
Careful, that's the inverse. Is e to the x. Yeah, if I take a derivative of e to the x, I just get e to the x back, right? And so that means if I take an integral of e to the x, I just get e to the x. So I'm going to get e to the x, and really, I'm going to get e to the x plus c. Okay, so this all tells me this is capital F of x, right? This all tells me then, plugging into this guy right here, well, the integral of 5e to the 5x dx, this is equal to, well, again, g of x is, we found out g of x has to be 5x, because that means g prime is this 5 left over. So we get the antiderivative of e to the x is e to the x plus c. So I'm going to get e to the 5x. That's this part. And then plus some constant. Okay. Yeah, g prime of x, yeah, we're undoing the chain rule, so we wouldn't expect to see a g prime, because the g prime comes from when we differentiate a composition, it gets spit out. Yeah.
What is this, like, five in that problem?
Yeah.
at the very beginning, the constant five,
Mhm.
just kind of like go away.
Yeah, exactly. Yeah, that 5 is g prime of x for us. And so the fact that that 5 shows up as g prime means that it just goes away on this side. Yeah, exactly. So the idea is if I differentiate this side, if I differentiate this, well, by the chain rule, when I differentiate this part right here, by the chain rule, I'll get e to the 5x times the derivative of the inside, which is times 5. And so that's where this is coming from.
Yeah, 'cause I noticed in that first one,
Yeah, yeah. There for especially for this first day of U substitution, I'm always going to give you stuff where the derivative of the inside is exactly in there. Now that's not always going to be the case. Sometimes we'll need to do a little bit more work, but this isn't really that far from what the actual U substitution method is. In fact, this is the actual method, but for very tailored problems, so we can see exactly how it's used. Okay, so let's look at one more before we go. All right, so dragging. Oh gosh, that could hurt. All right, so we want to integrate 4x to the 5th minus 7x all to the 7th times 20x to the 4th minus 7. Now, this problem would have been a nightmare to try and integrate before, right? The only thing that we know how to do is expand this and then integrate term by term, which is awful. But now we don't have to do that, hopefully, if this is a well-chosen U substitution problem. So again, we're hoping that we can write this in the form f of g of x, some function evaluated at some other function, times the derivative of that inside function. If we can do that, then this is just equal to an antiderivative of that outside function evaluated at the inside function. Okay, again, we're just undoing the chain rule. Okay, so looking here, is there a composition of functions in here? Is there some function evaluated at some other function? Yes, and what is the composition? Yeah, that's the outside function, exactly. It looks like, hopefully, f of x is x to the 7th, and what is g of x? 4x to the 5th minus 7x. And so that's going to be this part right here. That is f of g of x. Now we just have to hope that this is g prime of x. And if it is, then we're set. Then we can just say, all right, then the right-hand side is just this. Okay, well, what is g prime of x? (20x to the 4th minus 7). It's exactly what we wanted it to be able to use this method of undoing the chain rule. Okay. So then the only thing I need to know is what? On this side, I know g of x, I'm good. C is just some constant. What's the only thing I need to know? Yes, the only thing I need is big F. And what is big F? Perfect. Yeah, in general, big F is just the antiderivative or an antiderivative of little f, right? Well, if I want an antiderivative of little f, that tells me big F of x is, I could just take the indefinite integral, x to the 7th, with respect to x. And so big F of x is x to the 8th over 8 plus c if you want. It really doesn't matter when you add in the plus c. Okay. So then I have everything. I have big F. I know g has to be this 4x to the 5th minus 7x, because then g prime is 20x to the 4th minus 7, this stuff that's left over. Okay, so that means that the integral that we are interested in, the antiderivative, the general antiderivative of 4x to the 5th minus 7x all to the 7th times 20x to the 4th minus 7 dx is, well, big F is x to the 8th over 8. So I'm going to take g of x to the 8th over 8. I plug in g of x into big F. Okay, g of x is 4x to the 5th minus 7x. Raise that to the 8th, divide by 8, plus some number, some constant number, c. And we did it. So, U substitution. Why is it called U substitution? I haven't shown you yet why it's called U substitution. But this is what a U substitution, at the heart of it, what it is. It's just mostly recognizing, is this a composition? What is the inside function? And if that is the inside function, do I get the G prime that I want on the outside that's being multiplied? Okay. And again, for this first week, it's usually going to be the thing that you think is G of X is going to be G of X. In life, in the wild, this actually is, I know this seems like it's very specific, but in real life, it's very, very, very useful. It's amazing how often this kind of thing comes up where you're integrating a composition times the derivative of the inside, or at least times something close to the derivative of the inside that you can work with. Okay. So, I will, 2 minutes. I'm going to stop there. There's one problem on the quiz that I need to change, and then I'll open the quiz up in a couple of minutes, okay? So let me stop here. We're going to pick up here tomorrow, multiplying and dividing by a constant. So this is going to be for when your inside function, that derivative, is almost the g prime of x you want it to be, but it's off by a factor. Well, we'll be able to handle that pretty easily, okay? And it's just going to be by multiplying and dividing by a constant. Okay? So thank you all for being here. If you have any questions, you can stick around and ask me. I'm going to, again, open the quiz up in the next 15 minutes, okay? So make sure you get that done before tonight.